Welcome to the mysteries of the cosmos. In the vastness of the cosmos, with its countless stars and planets, a troubling question arises: if life is common, where is everyone else? This apparent contradiction between the high probability of extraterrestrial life and the lack of evidence is what we know as the Fermi paradox. Enunciated by physicist Enrico Fermi in 1950, this paradox has puzzled scientists and philosophers for decades. The universe is old, more than 13 billion years old, enough time for life to emerge and spread throughout the galaxy. Our Milky Way is home to hundreds of billions of stars, many of them with potentially habitable planets. If even a fraction of these worlds developed intelligent life, the galaxy would be buzzing with alien activity. Yet despite decades of searching, we have not detected any unequivocal signs of extraterrestrial intelligence. SETI, Search for Extraterrestrial Intelligence, programs have scanned the skies for artificial radio signals, with no success so far. One possible explanation is that intelligent life is extremely rare, a product of an improbable chain of evolutionary events. Another hypothesis suggests that advanced civilizations tend to self-destruct before reaching the capacity for interstellar colonization. The Great Filter proposes that there are critical barriers to evolution that few or no species manage to overcome. Could it be that we are alone because we are the first? Perhaps intelligent life is a recent phenomenon in cosmic history. Alternatively, advanced civilizations could exist but choose not to communicate, an idea known as the zoo hypothesis. Some theorists propose that alien signals could be out there, but we don't know how to detect or interpret them. The vastness of space and time also plays a crucial role. Civilizations could exist without overlapping in spacetime. The idea that we are in a computer simulation has been proposed as another solution to the paradox. Physical limits, such as the speed of light, could make galactic colonization impractical even for advanced civilizations. The rare Earth hypothesis suggests that conditions for complex life are exceptionally rare in the universe. Some argue that our definition of life or intelligence may be too narrow, leading us to miss alien signals. The possibility that advanced civilizations transcend physical form, becoming undetectable to us, is another intriguing theory. The concept of technospheres proposes that advanced civilizations could enclose themselves in structures that isolate them from the rest of the universe. The idea that aliens are actively avoiding us, perhaps to protect or observe us, is known as the orrery hypothesis. Some suggest that life might be common, but intelligence and technology might be extremely rare. The possibility that we are searching in the wrong place or at the wrong time cannot be ruled out. Our search could be misdirected. The mediocrity principle argues that we should not assume that we are special or unique in the universe. The paradox also raises questions about our future. Will we succeed in expanding beyond Earth, or will we face insurmountable obstacles? The cosmic silence could be a warning about the dangers facing advanced technological civilizations. Absence of evidence is not evidence of absence. Our search for extraterrestrial life has barely scratched the surface of the possibilities. Advances in the detection of exoplanets and the study of their atmospheres could soon revolutionize our search for biosignatures. The Fermi paradox challenges us to consider scales of time and space that defy our intuitive understanding. Could it be that life is common but technological intelligence is a fleeting phenomenon in the history of each planet? The possibility that there are forms of communication or technology completely beyond our understanding cannot be ruled out. The debate over the Fermi paradox has led to profound reflections on our place in the cosmos and the future of humanity. Some argue that the solution to the paradox could have existential implications for our species and our destiny. The idea that we might be the only technological civilization in our galaxy comes with enormous responsibility. On the other hand, the possibility that we are not alone but are unable to detect others raises fascinating questions about the limits of our knowledge. The Fermi paradox reminds us that in the search for extraterrestrial life, we must be open to possibilities that challenge our preconceptions. As our technology advances, our detection and analysis capabilities improve, offering new opportunities to solve this puzzle. Continued exploration of our solar system and beyond could provide crucial clues to unraveling this cosmic mystery. Regardless of the answer, the Fermi paradox will continue to be a catalyst for exploration, research, and philosophical reflection. Ultimately, the search for an answer to this paradox is also a search for self-understanding and our place in the vast cosmic tapestry. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to give the video a like. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. In the vastness of the cosmos, we search for extraterrestrial life. How do we recognize what might be fundamentally different from us? Scientists have developed criteria for identifying possible signs of life, from simple molecules to complex patterns of biological activity. The presence of liquid water tops the list of indicators, being a crucial solvent for biochemistry as we know it on Earth. Other solvents, such as liquid methane on icy moons, could support exotic life forms based on alternative chemistry. Atmospheric biomarkers, such as oxygen and methane in chemical imbalance, could reveal the presence of biological processes on exoplanets. The simultaneous detection of these gases on a rocky planet would be suggestive, since on Earth, their coexistence is maintained by life. Transit spectroscopy, which analyzes starlight filtered through an exoplanet's atmosphere, is key to searching for these chemical signals. In our solar system, we look for complex organic molecules, such as amino acids or nucleotides, the building blocks of life on Earth. Martian rovers analyze rock and soil samples for organic molecules and signs of past or present habitability. Chirality, the preference for left or right-handed molecules in biological systems, could be a distinctive signature of life on other worlds. The distribution patterns of certain compounds can be revealing. Life concentrates elements in ways that abiotic chemistry cannot replicate. Detecting photosynthetic pigments on other planets could indicate organisms that harness stellar energy, like terrestrial plants. In dark environments, such as the subsurface oceans of icy moons, chemosynthesis could sustain ecosystems, leaving unique imprints. Biogeochemical cycles, like that of carbon on Earth, could manifest themselves similarly on other worlds, suggesting complex ecosystems. Seasonal variation in an exoplanet's atmospheric composition could indicate biological activity, as occurs with terrestrial vegetation. We look for cellular structures, microfossils, or biopolymers that could indicate the presence of living or extinct organisms. Future space missions with advanced microscopy and spectroscopy could reveal microscopic structures of biological processes. Unexplained chemical or energetic gradients in planetary environments could indicate the presence of active biological metabolism. In the search for intelligent life, we scan the sky for radio or laser signals unexplained by known natural phenomena. Projects like Breakthrough Listen use radio telescopes to search for emissions that could indicate advanced alien technology. Technosignatures, such as industrial pollution or megastructures, could reveal the presence of technologically advanced civilizations. Agnostic biosignatures look for patterns that suggest complex, self-sustaining processes without assuming a specific biochemistry. Astrobiology considers that life can exist in forms radically different from those on Earth, requiring innovative approaches. Future telescopes could detect signs of life in the atmospheres of terrestrial exoplanets in the habitable zone of their stars. The study of extreme terrestrial environments sheds light on how life might adapt and leave its mark in alien conditions. False positives are a challenge. Geological or chemical processes can mimic signs of life, requiring careful analysis. The presence of organic compounds in comets and asteroids suggests that the basic ingredients for life may be common. Terrestrial extremophiles expand our understanding of the limits of life, guiding the search in hostile extraterrestrial environments. Silicon-based life, although speculative, is not ruled out, expanding the range of potential biomarkers to consider. Artificial intelligence revolutionizes our ability to analyze data for subtle patterns that could indicate life. Detecting extraterrestrial life, especially if it is very different from Earth's, would revolutionize our understanding of biology and the universe. This challenge forces us to question our most basic assumptions about what life is and how it manifests itself in the cosmos. Collaboration across disciplines is crucial to understanding potential signs of life on other worlds. This quest is both a scientific adventure and an exercise in cosmic imagination and humility. By refining techniques and expanding the search, we increase the chances of a discovery that redefines our understanding of the universe. Finding life beyond Earth, even a simple one, would have profound philosophical, scientific, and possibly theological implications. Comparative astrobiology studies how life might develop in diverse planetary environments, guiding the search for biosignatures. Finding extinct life on other worlds, such as Mars, poses unique challenges and could reveal crucial information about planetary evolution. The possibility of multiple independent origins of life in the universe is a fascinating concept that scientists consider. We must be prepared for the unexpected. Alien life could challenge our most fundamental understandings of biology. This quest connects us with profound questions about our origins, our future, and our place in the vast cosmos. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. Einstein's theory of relativity shook the foundations of physics, challenging our perception of the universe and redefining time and space. Before Einstein, time was believed to flow uniformly for everyone, but relativity showed that time is relative and can vary depending on the observer. Imagine two twins, one stays on Earth, the other travels in a spaceship at near light speeds. Upon returning, the traveling twin will have aged less. This phenomenon, time dilation, has been verified with atomic clocks on satellites and is crucial for the precise functioning of GPS. Relativity taught us that space and time are linked, forming spacetime, a four-dimensional fabric that can be deformed by gravity. This deformation explains the orbits of planets and phenomena such as black holes, where gravity is so intense that not even light escapes. The equation E=E² reveals the equivalence between mass and energy, laying the foundation for understanding processes such as nuclear fusion in stars. Einstein also predicted gravitational waves, disturbances in the fabric of spacetime first detected in 2015. Relativity changed our view of the cosmos and has practical applications in technologies such as nuclear power and positron emission tomography. The idea that the speed of light is constant and a universal limit challenged our intuition, but has been confirmed by precise experiments. The concept of time flowing at different rates depending on motion or gravity seems strange, but it is fundamental to modern physics. Einstein showed that simultaneity is relative. Events that are simultaneous for one observer may not be for another, challenging the idea of a universal now. Special relativity, from 1905, deals with objects at constant speed. General relativity, from 1915, incorporates gravity. The curvature of spacetime explains planetary orbits. Planets follow the geometry of warped space, not a mysterious force. The concept of curved spacetime replaced the Newtonian idea of gravity as a force at a distance, more accurately describing the universe. The theory predicts that a clock on a mountain runs faster than one at sea level, due to the difference in the Earth's gravitational field. This time variation due to gravity, although small on Earth, is crucial for the accuracy of satellite navigation systems. Einstein anticipated the gravitational redshift. Light escaping from an intense gravitational field loses energy and its wavelength increases. This effect is observed in the light of massive stars and is most pronounced near black holes, where time appears to stop to outside observers. General relativity predicts black holes, regions where gravity is so intense that nothing, not even information, escapes its horizon. These enigmatic objects, once considered mathematical curiosities, are now known to be common throughout the universe, even at the center of our galaxy. Einstein's theory explains the precession of Mercury's perihelion, a phenomenon that Newtonian physics did not justify, confirming relativity. A surprising prediction is that gravity acts as a lens, bending the light from distant objects. This effect is used to study distant galaxies. The idea of curved spacetime led to the prediction of gravitational waves, cosmic ripples produced by events such as the merger of black holes. Its detection in 2015 by LIGO confirmed another of Einstein's predictions and inaugurated a new era in astronomy, allowing us to hear the universe. Relativity also predicted the expansion of the universe, an idea initially rejected by Einstein but confirmed by Hubble, leading to the concept of the Big Bang. The equivalence principle states that the effects of gravity are indistinguishable from those of acceleration, unifying two different concepts. This led Einstein to conclude that light must bend in a gravitational field, a prediction confirmed in a solar eclipse in 1919. Special relativity introduced that mass increases with speed, explaining why it is impossible to accelerate particles to the speed of light. This relationship between mass and energy is key in particle physics and explains phenomena such as the production of particle-antiparticle pairs in accelerators. Einstein also predicted white holes, the theoretical opposite of black holes, although no evidence of their existence has yet been found. Relativity suggests Einstein-Rosen bridges or wormholes, hypothetical tunnels that could connect distant regions or parallel universes. Although travel to the past is controversial, the theory in principle allows for travel to the future. Travel near the speed of light could jump forward. The theory has cosmological implications, suggesting that the universe could be finite but edgeless, like a sphere, challenging our spatial intuition. The concept of proper time shows that the time between two events depends on the path followed, leading to the famous twin paradox. Relativity predicts that a freely falling object does not feel its weight, an idea Einstein described as the happiest thought of my life. Relativistic effects, imperceptible in everyday life, are crucial in technologies such as accelerators, where particles reach near light speeds. The theory suggests rotating reference frames, leading to effects such as inertial frame drag, observed in satellites orbiting the Earth. Relativity predicts that time flows more slowly near massive objects, an effect precisely confirmed in ground-based experiments. This time difference due to gravity affects GPS. Satellite clocks must be adjusted to compensate for relativistic effects and maintain accuracy. Einstein showed that there is no universal now. Simultaneous events for one observer may not be simultaneous for another in relative motion. The theory introduced Minkowski spacetime, a mathematical representation that unifies space and time into a four-dimensional continuum. This led to the view of the universe as a 4D block where past, present and future coexist, challenging our perception of the flow of time. Einstein predicted gravitational time dilation. A clock on a massive planet runs slower than one in deep space. This effect is dramatic near black holes, where time can slow down enormously, leading to the concept of time freeze. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. Spacetime is the canvas on which the entire history of the universe is painted, uniting the concepts of space and time into a single entity. This revolutionary union, proposed by Einstein, fundamentally changed our understanding of reality and the structure of the cosmos. Imagine spacetime as a rubber band. Massive objects, like stars and planets, create depressions in this cosmic fabric. These depressions not only affect the motion of other objects, but also the flow of time, which slows down in strong gravitational fields. In spacetime, movement through space affects the passage of time. The faster you move, the slower time passes for you. This effect, although imperceptible in everyday life, is crucial in technologies such as GPS, where satellites must constantly adjust their clocks. The curvature of spacetime explains gravity. Planets are not attracted by the sun, but rather follow trajectories in this warped fabric. This geometric view of gravity solved puzzles such as the orbit of Mercury, which Newtonian physics could not fully explain. Spacetime isn't static, it can ripple and vibrate. These ripples, predicted by Einstein, are gravitational waves. First detected in 2015, gravitational waves open a new window for observing violent cosmic events. In the fabric of spacetime, past, present, and future coexist, challenging our linear perception of time. This idea of the block universe suggests that time is a dimension like space, and that our now is just a slice of this totality. Spacetime can stretch. The expanding universe does not imply that galaxies are moving through space, but that space itself is expanding. This expansion, discovered by Hubble, led to the concept of the Big Bang and changed our understanding of the origin and evolution of the universe. In regions of extreme gravity, such as black holes, spacetime warps so much that our usual physical laws break down. Near the event horizon of a black hole, time slows down dramatically for an outside observer, almost coming to a standstill. Spacetime connects not only places but also events. What happens here and now can influence the there and then of the universe. This causal connection defines our light cone, the region of spacetime that we can affect or that can affect us. The structure of spacetime imposes fundamental limits. Nothing can travel faster than light, which preserves causality in the universe. This cosmic speed limit ensures that the effect never precedes the cause, maintaining the logical consistency of events. The concept of spacetime resolves apparent paradoxes. Two events that are simultaneous for one observer may not be so for another observer in motion. This relativity of simultaneity shows that there is no universal now, but rather it depends on the observer's frame of reference. In the fabric of spacetime, matter and energy are interchangeable, as expressed in Einstein's famous equation, and equal to E squared. This equivalence explains phenomena such as the creation of particles in accelerators and the immense energy released in nuclear reactions. Spacetime may have more dimensions than we perceive. Theories such as string theory propose additional, coiled dimensions. These extra dimensions, although directly unobservable, could explain mysteries such as quantum gravity and the unification of fundamental forces. The curvature of spacetime affects not only matter but also light. This effect, called gravitational lensing, allows us to see distant galaxies. Using this phenomenon, astronomers can observe and study objects that would otherwise be too faint or distant to detect. The fabric of spacetime is not uniform. It can have wrinkles or folds that could manifest as wormholes. These hypothetical tunnels in spacetime could connect distant regions of the universe, although their actual existence is still speculative. The structure of spacetime near a black hole challenges our intuition. Space and time can exchange roles. Inside a black hole, time becomes a spatial dimension, and movement into the future becomes as inevitable as falling downward. Spacetime not only curves, but can also twist. This effect, called frame dragging, has been measured near Earth. Frame drag implies that an object in close orbit around a massive rotating body will be dragged in the direction of the body's rotation. The geometry of spacetime determines the fate of the universe. Its overall curvature influences whether the cosmos will expand eternally or collapse. Recent measurements suggest that the universe is flat on large scales, which has profound implications for its future evolution. The concept of unified spacetime resolves the paradox of the now in a vast universe. Every point in the cosmos has its own local present. This locality of the present reconciles our experience of the now with the vastness of the universe and the limits imposed by the speed of light. In the fabric of spacetime, even the vacuum is not really empty. Quantum fluctuations constantly create and destroy particles. These quantum vacuum fluctuations can have measurable effects, such as the Casimir force, and could have played a role in the origin of the universe. The structure of spacetime may not be continuous at tiny scales. Some theories propose a quantum foam at the most fundamental level. This granular nature of spacetime at the Planck scale could resolve conflicts between general relativity and quantum mechanics. Spacetime not only connects events, but also defines causality. The cause-effect relationship is intrinsically linked to its structure. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. Time travel has fascinated humanity for centuries, inspiring countless works of fiction and scientific speculation. But what does science really say about the possibility of time travel? The answer is more complex than we might imagine. Einstein's theory of relativity opened the door to the theoretical possibility of time travel, challenging our understanding of the flow of time. According to relativity, time is not absolute but relative, and can expand or contract depending on speed and gravity. This time dilation is real and has been confirmed experimentally. Clocks on GPS satellites must be adjusted to compensate for these relativistic effects. A traveler moving at speeds close to the speed of light would experience time slower, allowing him to jump into the future upon returning to Earth. This journey into the future is theoretically possible and does not violate any known laws of physics, although practical limitations make it currently unfeasible. Traveling back in time, however, presents much greater challenges and could conflict with fundamental principles of physics. Time paradoxes, such as the famous grandfather paradox, pose logical problems that question the feasibility of time travel. Some theories propose that these paradoxes could be resolved through parallel universes or alternative timelines. Wormholes, hypothetical tunnels in spacetime, have been proposed as possible mechanisms for time travel. However, keeping a wormhole open would require exotic forms of matter with properties that defy our current understanding. The idea of closed time-like curves in general relativity suggests the theoretical possibility of time travel, but with serious physical limitations. Some physicists argue that Novikov's self-consistency principle could prevent paradoxes by ensuring that the past cannot be altered. Quantum mechanics adds another layer of complexity to the concept of time travel, suggesting possible solutions to some classical paradoxes. Quantum post-selection proposes that particles could travel backward in time, but only in a way that avoids creating paradoxes. Recent experiments have explored the behavior of entangled particles in time, offering fascinating insights into quantum causality. Although these experiments do not allow information to be sent back in time, they challenge our conventional understanding of the direction of time. The idea of late signals in quantum physics suggests that, in a sense, the future could influence the past at the subatomic level. However, these quantum effects do not translate directly into the possibility of macroscopic time travel as we imagine it in fiction. Stephen Hawking's chronological protection theorem proposes that the laws of physics might prohibit travel to the past to avoid paradoxes. This hypothesis suggests that the universe has intrinsic mechanisms to prevent the creation of time machines, preserving causality. Thermodynamics and the arrow of time present another obstacle: how to reconcile travel to the past with the inevitable increase in entropy. Thermodynamic irreversibility seems to be in direct conflict with the idea of being able to freely go back in time. Some cosmological models, such as Gödel's universe, theoretically allow time travel, but they do not seem to describe our actual universe. These models are valuable as theoretical exercises, but they do not offer a practical path to building time machines. The search for time travelers from the future has been unsuccessful so far, which some consider indirect evidence of its impossibility. However, absence of evidence is not evidence of absence, and the possibility of time travel remains a topic of active research. Particle accelerators like the LHC have been the subject of speculation about the creation of micro-black holes or time distortions. Although these experiments have not produced evidence of time travel, they continue to expand our understanding of spacetime. The idea of protected chronology suggests that any attempt to create a time machine would be thwarted by radiation feedback. This radiation would be amplified until it destroyed the time travel mechanism before it could work, preserving causality. The concept of cosmic censorship proposes that nature hides singularities where the laws of physics break down, possibly including time machines. This hypothesis, although unproven, could explain why we do not observe large-scale causality violations in the universe. Tipler loops, or infinitely long, rotating cylinders, could theoretically create closed time paths, allowing travel to the past. However, the construction of such objects is physically impossible, requiring infinite length and resistance to extreme gravitational forces. The possibility of sending information back in time via faster-than-light particles, such as hypothetical tachyons, remains purely theoretical. So far, no evidence has been found for the existence of tachyons, and their presence could violate fundamental principles of physics. The quantum grandpa killer experiment proposes resolving temporal paradoxes through quantum mechanics in parallel universes. This interpretation suggests that time travel might be possible without creating paradoxes, but at the cost of creating new timelines. The idea that time might be an emergent illusion, proposed by some theories of quantum gravity, questions the very nature of time travel. If time is not fundamental but emergent, the concept of time travel might need a complete redefinition. Causal loops in theoretical physics suggest situations where an event is its own cause, challenging our understanding of causality. Although theoretically possible in some solutions to Einstein's equations, these loops present significant philosophical and logical challenges. The search for a theory of everything that unifies quantum mechanics and general relativity could provide new insights into time travel. Until then, the possibility of time travel remains one of the most intriguing and challenging enigmas of modern physics. While travel to the future is theoretically possible, travel to the past remains a topic of intense scientific debate and speculation. The continued exploration of these concepts not only expands our knowledge of the universe, but also challenges our understanding of time itself. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. Wormholes, fascinating theoretical constructs, represent possible shortcuts through spacetime, capturing the imagination of scientists and the public. These hypothetical tunnels could connect distant regions of the universe or even different universes, challenging our understanding of the cosmos. The concept was first introduced in 1935 by Einstein and Rosen as a mathematical solution to the equations of general relativity. Originally called Einstein-Rosen bridges, these theoretical objects arose as an unexpected consequence of the theory of relativity. A wormhole can be visualized as a tunnel with two entrances, each at a different point in spacetime, potentially very far apart. In theory, these passages could allow faster-than-light travel between distant points, though without actually violating the cosmic speed limit. The structure of a wormhole resembles two funnels connected at their narrowest points, forming a bridge across spacetime. This peculiar geometry could allow a traveler to traverse vast cosmic distances in much less time than required by conventional routes. However, wormholes present formidable challenges. Most mathematical solutions show them to be extremely unstable. A typical wormhole would collapse almost instantly, long before anything could pass through it, due to radiation feedback. To keep a wormhole open, an exotic form of matter with negative energy would be needed, a concept that challenges our current understanding. This exotic matter would have anti-gravitational properties, counteracting the wormhole's natural tendency to collapse on itself. Although the existence of negative energy is supported by quantum effects such as the Casimir effect, producing it in sufficient quantities currently seems impossible. Wormholes also pose intriguing possibilities for time travel, as they could connect not only distant points, but also different eras. A wormhole connecting the present with the past could, in theory, allow travel to the past, although this entails significant temporal paradoxes. The grandfather paradox is a classic example. What would happen if someone traveled back in time and prevented the birth of their own parents? Some physicists propose that self-consistency principles or the creation of parallel universes could resolve these paradoxes, but the debate continues. Microscopic wormholes could exist at the quantum level, forming part of the so-called quantum foam on the smallest scales of spacetime. These micro-wormholes, if they exist, would be too small and short-lived to be detected or used for macroscopic travel. The search for wormholes in the observable universe is an active area of astronomical research, although so far without conclusive results. Some theories suggest that supermassive black holes at the centers of galaxies could be connected by wormholes. This idea, although speculative, could explain some of the enigmatic properties observed in active galactic nuclei. Wormholes also play an important role in advanced cosmological theories, such as string theory and loop quantum gravity. In these theoretical frameworks, wormholes could be fundamental components of the structure of spacetime at subatomic scales. The possibility of artificially creating wormholes has been theoretically explored, although it is far from being feasible with current technology. Some physicists have proposed experiments to detect mini wormholes or their effects, using advanced particle physics techniques. The detection of gravitational waves has opened up new possibilities for searching for indirect evidence of wormholes in the universe. Unusual gravitational signals could, in theory, provide clues to the existence of these exotic cosmic objects. Wormholes have also inspired concepts of advanced space propulsion, such as the science fiction warp drive. Although purely theoretical, these concepts explore how manipulation of spacetime could enable rapid interstellar travel. The idea of using wormholes for instant interstellar communication has been proposed, although it faces the same challenges as physical travel. If feasible, wormholes could revolutionize our understanding of the universe and our ability to explore it. The study of wormholes is intertwined with fundamental questions about the nature of space, time, and causality in the universe. These investigations challenge the limits of our knowledge and force us to reconsider basic concepts of physics and cosmology. Although stable, macroscopic wormholes seem unlikely, their study continues to provide valuable theoretical insights. Research on wormholes has led to advances in our understanding of quantum gravity and the structure of spacetime. Some scientists speculate that wormholes could play a role in phenomena such as long-distance quantum entanglement. This connection between wormholes and quantum phenomena could provide new ways to unify general relativity and quantum mechanics. The possibility that our universe is connected to others through cosmic wormholes is a fascinating idea in modern cosmology. This notion of a connected multiverse could explain the astonishing precision with which the fundamental constants of our universe appear to be finely tuned, making the existence of life possible. Although traversable wormholes remain science fiction, they continue to inspire both scientific research and popular imagination. Its study reminds us that the universe may be stranger and more wonderful than we can imagine, prompting us to explore the limits of the possible. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. The arrow of time is a fascinating concept that describes the seemingly unidirectional direction in which events flow in our universe. This fundamental phenomenon raises an intriguing question: why do we experience time as always moving forward and never backward? Unlike space, where we can move freely in any direction, time seems to have a fixed and irreversible direction. This temporal asymmetry is evident in our daily lives. We can remember the past, but not the future. We see objects break, but they never spontaneously reassemble. The arrow of time manifests itself in various aspects of physics, each offering a unique perspective on this cosmic enigma. The thermodynamic arrow of time is perhaps the best known, based on the second law of thermodynamics and the concept of entropy. Entropy, a measure of disorder in a system, tends to increase over time in closed systems, providing a clear direction to the flow of time. This principle explains why it is easy to mix paint of different colors, but impossible to separate them once mixed without external intervention. The psychological arrow of time refers to our subjective perception of the passage of time and our ability to distinguish between past and future. Our memories are formed and stored in one direction, creating a sense of personal history that flows from the past to the future. The cosmological arrow of time is related to the expansion of the universe, which provides a clear direction from the Big Bang into the future. This cosmic expansion creates a fundamental asymmetry in the history of the universe, clearly distinguishing between its compact past and its expansive future. The quantum arrow of time emerges from quantum mechanics, where the act of measurement introduces irreversibility into previously reversible systems. The collapse of the wave function during a quantum measurement creates a distinctive before and after, contributing to our perception of the flow of time. The electromagnetic arrow of time is observed in electromagnetic radiation, where waves expand into the future but do not contract from the past. This behavior of light and other electromagnetic waves reinforces the apparent direction of time in our observations of the universe. The causal arrow of time refers to the sequence of cause and effect that we observe in events, where causes always precede their effects. This unidirectional causality is fundamental to our understanding of the world and appears to be deeply rooted in the structure of the universe. The paradox of the arrow of time arises when we consider that the fundamental laws of physics are largely reversible in time. At the microscopic level, many physical equations work the same forward or backward in time, in contrast to our macroscopic experience. This discrepancy between the time symmetry of physical laws and the asymmetry observed in the real world is a subject of intense scientific debate. Some physicists argue that the arrow of time could be an emergent property, arising from low-entropy initial conditions in the early universe. The baby universe hypothesis suggests that our cosmos began in an exceptionally ordered state, setting the stage for increased entropy. This idea connects the arrow of time with cosmology, proposing that the direction of time is intrinsically linked to the evolution of the universe. The concept of block time and relativity challenges our perception of a flowing time, suggesting that past, present, and future coexist. In this view, the arrow of time might be more a feature of our consciousness than a fundamental property of the physical universe. Black hole thermodynamics, developed by Stephen Hawking and others, has provided new insights into the nature of time and entropy. Black holes appear to represent states of maximum entropy, potentially offering clues to the ultimate fate of time's arrow. The idea of time reversal in quantum systems has been explored experimentally, showing behaviors that appear to defy the arrow of time. These experiments, although limited to microscopic scales, suggest that the irreversibility of time might not be absolute at all levels. The arrow of time also has profound philosophical implications, questioning concepts such as free will and the nature of reality. If the future is determined by the past, how do we reconcile this with our sense of making free choices and affecting the course of events? The block universe hypothesis proposes that all moments in time exist simultaneously, and our perception of temporal flow is illusory. This view challenges our intuition, but it could resolve some paradoxes related to the nature of time in modern physics. The search for a unified theory of physics could provide new insights into the arrow of time and its fundamental origin. Some physicists speculate that a theory of quantum gravity could reveal the ultimate source of the time asymmetry we observe. The connection between the arrow of time and the complexity of the universe is an active area of research in physics and cosmology. It has been proposed that the increase in cosmic complexity could be an alternative manifestation of the arrow of time, parallel to the increase in entropy. The possibility of islands of time reversibility in an expanding universe has been theorized, suggesting regions where time might flow differently. Although highly speculative, this concept illustrates the complexity and potential surprises that might still exist in our understanding of time. The arrow of time also relates to the problem of structure formation in the universe, from galaxies to life itself. The tendency toward increasing entropy seems to contradict the formation of complex systems, a puzzle known as the Loschmidt problem. Resolving this apparent contradiction between increasing entropy and the evolution of complexity is a central challenge in modern physics. The arrow of time raises fundamental questions about the nature of the universe. Is the flow of time an illusion or a fundamental property of reality? As we explore these questions, we come closer not only to a better understanding of time, but also of the very nature of the cosmos. The study of the arrow of time continues to challenge our intuitions and push the boundaries of theoretical and experimental physics. Understanding why time flows the way it does could be key to unraveling some of the deepest mysteries of the universe. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. The question of whether time can end takes us to the limits of our cosmological knowledge and confronts us with dizzying concepts. To understand whether time can have an end, we must first understand its nature and how it is intertwined with the fate of the universe itself. The concept of end of time can be interpreted in several ways, each with profound implications for our understanding of the cosmos. One possibility is that time ends with the end of the universe, which leads us to consider possible scenarios of cosmic fate. The Big Crunch model proposes that the universe could eventually stop expanding and collapse in on itself, possibly ending time. In this scenario, spacetime would contract to a singular point, similar to the Big Bang but in reverse, potentially marking the end of time. Another scenario, the Big Freeze or heat death of the universe, suggests a future where the universe expands eternally, gradually cooling. In this case, time could continue indefinitely, but in a universe that is increasingly cold, dark, and lacking in complex structures. The Big Rip hypothesis proposes a more dramatic ending, where the accelerated expansion of the universe eventually tears all matter apart. This extreme scenario could lead to the dissolution of spacetime itself, potentially marking a definitive end to the concept of time. Some cosmological models suggest the possibility of a cosmic rebound, where the universe oscillates between expansions and contractions. In this case, time might not have a definitive end, but rather go through cycles of cosmic rebirth, challenging our linear notion of time. String theory and brain models propose the existence of multiple universes, further complicating the question of the end of time. In a multiverse, the end of time in our universe might not mean the end of time in an absolute sense, but only in our local context. Quantum mechanics adds another layer of complexity, suggesting that time might behave fundamentally differently at subatomic scales. Some physicists theorize that at the quantum level, time might not be continuous but discrete, composed of indivisible units called time quanta. The idea that time might be an emergent, rather than fundamental, property of the universe has gained attention in some theories of quantum gravity. If time is emergent, its end might not make sense at a fundamental level, but rather be an aspect of our macroscopic experience. The concept of eternity in modern physics does not necessarily imply infinite time, but rather the absence of time under certain extreme conditions. For example, inside a black hole, the equations of general relativity suggest that time might cease to have meaning as we understand it. The notion of imaginary time, proposed by Stephen Hawking, offers a way around the Big Bang singularity and the concept of a beginning of time. In this model, time behaves like a spatial dimension near the Big Bang, eliminating the need for a defined beginning or end of time. Thermodynamics and entropy play a crucial role in our understanding of the future of time and the universe. The inevitable increase in entropy suggests an arrow of time pointing toward a state of maximum disorder, but not necessarily to a defined end. Some physicists speculate about the possibility of islands of time, regions of the universe where time might behave differently. These hypothetical regions could experience time in different ways, or even exist outside of our conventional time flow. Quantum cosmology explores scenarios where the universe could exist in a superposition of states, including different times simultaneously. This perspective challenges our classical notion of a single, universal time, suggesting a much more complex and multifaceted reality. The idea of a cyclical time has resurfaced in some modern theories, proposing that the universe could go through infinite cycles of existence. In this scenario, time would have no end, but would repeat itself eternally, although each cycle might be fundamentally different from the previous one. The concept of eternal time in some interpretations of quantum mechanics suggests that all possible moments could exist simultaneously. This vision of the quantum block universe challenges our linear perception of time, suggesting that the end might be merely an illusion of our consciousness. The possibility of additional time dimensions, proposed in some string theories, adds another layer of complexity to the question of the end of time. Multiple temporal dimensions could allow for more complex temporal structures than our linear concept of past, present, and future. The role of consciousness in the perception of time raises philosophical questions about whether the end of time has meaning without an observer. Some argue that time, as we experience it, might be a construct of our mind, and its end might not make sense outside of consciousness. The holographic universe theory suggests that our three-dimensional universe could be a projection of information stored on a two-dimensional surface. In this model, time could be an emergent property of this information, questioning the fundamental nature of time and its possible ending. Advances in particle physics and the search for a theory of everything could provide new insights into the ultimate nature of time. Experiments at large colliders and precise astronomical observations continue to provide data that could solve the mystery of the fate of time. The possibility that the universe is infinite in extent raises questions about whether time might also be infinite in duration. A spatially infinite universe could imply the existence of identical copies of ourselves, repeating history infinitely in space and time. The idea of a false vacuum in cosmology suggests that our universe may be in a metastable state, susceptible to a cosmic phase transition. Such a transition could fundamentally alter the laws of physics and the nature of time, possibly leading to its end as we understand it. The concept of quantum information and its conservation could have profound implications for the ultimate fate of time and information in the universe. Some physicists propose that information is never truly lost, which could mean that the end of time does not imply the total loss of cosmic history. The search for a unified theory of quantum gravity remains crucial to truly understanding the fate of time and the universe. Such a theory could reveal whether time is truly fundamental or emergent, and whether it has a definitive end or continues eternally in some form. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. In the depths of the cosmos, a mystery lurks that defies our understanding: dark matter, an invisible substance that dominates the universe. Imagine a universe where what we see is only a fraction of what actually exists, a cosmos where the invisible outnumbers the visible by astonishing proportions. Dark matter, elusive and enigmatic, resists our attempts to detect it directly, but its presence is felt through its gravitational effects. Entire galaxies spin at speeds that defy the laws of known physics, held together by the invisible force of this mysterious substance. Galaxy clusters, vast collections of galaxies, reveal the presence of dark matter through the distortion of light passing around them. What exactly is dark matter? Scientists speculate that it could be composed of exotic particles not yet discovered in our laboratories. WIMPs, or weakly interacting massive particles, are one of the leading candidates in the search for the nature of dark matter. Underground laboratories, shielded from cosmic radiation, house ultra-sensitive detectors designed to capture the elusive signals of these particles. Particle accelerators seek to create dark matter under controlled conditions, hoping to shed light on its fundamental nature. MON theory, or modified Newtonian dynamics, proposes a bold alternative. Perhaps it's not matter that's missing, but our understanding of gravity. The world's most advanced telescopes scan the night sky, mapping the distribution of dark matter through its gravitational effects. The Hubble Space Telescope has captured striking images of how dark matter bends light from distant galaxies, creating cosmic lenses. These gravitational lenses allow us to see further into the universe than we ever imagined, revealing incredibly distant galaxies. Dark matter plays a crucial role in the formation of cosmic structures, acting as the invisible scaffolding upon which galaxies are built. Without it, the universe as we know it would not exist. Galaxies would have been torn apart long ago by their own rotational forces. Dark matter filaments, vast structures that stretch for millions of light years, form the cosmic web that connects galaxy clusters. This cosmic web, invisible to the naked eye, is revealed through computer simulations and observations of the large-scale distribution of galaxies. The search for dark matter has taken us to the depths of the Earth and to the far reaches of space, uniting scientists from diverse disciplines. Astrophysicists, particle physicists, and cosmologists are working together, combining observations of the sky with experiments on Earth to solve this puzzle. Each new observation and experiment brings us a little closer to understanding the nature of this mysterious substance that dominates our universe. Dark matter challenges our preconceived notions about the composition of the cosmos, forcing us to rethink the foundations of modern physics. Could dark matter be the key to unifying quantum mechanics and general relativity, the two major theories of current physics? Some scientists speculate that dark matter could be evidence of parallel universes, interacting with our own only through gravity. The Axion hypothesis proposes ultralight particles as components of dark matter, offering another avenue for research and experimentation. Gravitational wave detectors, such as LIGO, could provide new ways to study dark matter through its effects on cosmic events. ESA's Euclid space mission is designed to map the distribution of dark matter in the universe with unprecedented precision. CERN's Large Hadron Collider continues its search for dark matter particles, exploring ever higher energies in its experiments. The lack of direct detection has led some scientists to propose even more exotic theories about the nature of dark matter. Could it be composed of primordial black holes, formed in the earliest moments of the universe after the Big Bang? The interaction between dark matter and normal matter could be key to understanding the formation of the first stars and galaxies in the universe. The study of brown dwarfs, objects halfway between stars and planets, could provide clues about the nature of dark matter. Satellites orbiting the Milky Way provide a natural laboratory for studying the effects of dark matter on small gravitational systems. The distribution of dark matter in dwarf galaxies challenges our current models, suggesting that we are still missing something fundamental in our understanding. The Xenon project, located under a mountain in Italy, uses ultra-pure liquid xenon to try to detect the interactions of dark matter particles. Every negative result in a direct search forces us to rethink our assumptions and seek new, innovative approaches to research. Dark matter could be the key to understanding the asymmetry between matter and antimatter in the universe, one of the great mysteries of cosmology. Neutrino telescopes, such as IceCube in Antarctica, could provide new ways to indirectly detect the presence of dark matter. The search for dark matter pushes us to the limits of technology, driving the development of increasingly sensitive and sophisticated detectors. The study of dark matter has implications that go beyond astrophysics, touching fields such as particle physics and quantum cosmology. As our understanding evolves, dark matter continues to challenge us, reminding us how much remains to be discovered in the vast cosmos. Solving this mystery could revolutionize our understanding of the universe, breaking new ground in 21st century physics and cosmology. Meanwhile, dark matter remains the invisible glue that holds our universe together, a mystery that still eludes and fascinates us. As we continue our exploration, dark matter reminds us that the universe is stranger and more wonderful than we ever imagined. The mystery continues to inspire new generations of scientists, driving us to explore the limits of our cosmic knowledge relentlessly. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. In the vast expanses of the cosmos, an enigmatic force is reshaping the fate of the universe, dark energy, a mystery that defies our understanding. Imagine an invisible energy permeating every corner of space, pushing galaxies away from each other at ever-increasing speeds. The discovery of the accelerated expansion of the universe in 1998 shook the foundations of cosmology, revealing the existence of dark energy. This mysterious force constitutes approximately 70% of the total energy in the universe, far exceeding visible and dark matter combined. Unlike other forms of energy, dark energy does not clump together or dilute as the universe expands. It maintains a constant density in space. Scientists speculate that dark energy could be an intrinsic property of the vacuum of space, a kind of vacuum energy predicted by quantum mechanics. Another possibility is that it represents a new energy field, similar to the Higgs field, but with unique properties that we do not yet fully understand. The cosmological constant, originally proposed by Einstein and later discarded, has resurfaced as a possible explanation for the nature of dark energy. However, theoretical calculations of vacuum energy predict an astronomically larger value than observed, creating one of the greatest enigmas in physics. This discrepancy, known as the cosmological constant problem, suggests that we are missing something fundamental in our understanding of the universe. Observations of distant supernovae have been crucial for measuring the effects of dark energy, revealing how it has influenced cosmic expansion over time. The James Webb Space Telescope promises to provide even more precise data on the history of the universe's expansion and the nature of dark energy. Missions such as ESA's Euclid and the Vera Rubin Observatory are specifically designed to study the effects of dark energy on a large scale. These missions will map the distribution of galaxies in the universe, searching for clues about how dark energy has shaped cosmic structure over time. Dark energy raises fundamental questions about the ultimate fate of the universe. Will it continue to expand forever, or could it one day reverse itself? The Big Rip scenario suggests that if dark energy grows stronger over time, it could eventually tear apart all matter, even atoms. On the other hand, if dark energy weakens, the expansion could slow down and even reverse, leading the universe to a final big crunch. Some theoretical models propose that dark energy could be dynamic, changing its intensity over cosmic time in as yet unpredictable ways. Quintessence, an energy field that varies in space and time, is one of the most intriguing proposals to explain the nature of dark energy. Understanding dark energy could be the key to unifying quantum physics and general relativity, solving one of the greatest challenges of modern physics. Experiments on Earth, such as the search for fifth-order forces, attempt to detect subtle deviations from gravity that could reveal the nature of dark energy. The possibility that dark energy is related to extra dimensions of spacetime has led to fascinating theories at the frontier of theoretical physics. Some scientists speculate that dark energy could be evidence of the existence of multiple universes, each with its own physical laws and constants. The study of dark energy forces us to rethink fundamental concepts such as time, space, and the very nature of physical reality. Large-scale computer simulations of the universe are helping scientists predict how dark energy will shape cosmic structure in the distant future. As galaxies move away from each other faster and faster, there will come a time when most of the observable universe will be beyond our visual range. This expanding cosmic horizon raises profound questions about the limits of human knowledge and our ability to study the distant universe. Dark energy could have surprising implications for string theory and other theories that seek a unified description of all fundamental forces. Advances in particle physics, such as studies of the Higgs boson, could provide crucial clues about the nature of vacuum energy and dark energy. The possibility that dark energy is related to dark matter has led to unified theories that attempt to explain both phenomena with a single mechanism. The study of dark energy is driving the development of new observation technologies, from advanced space telescopes to gravitational wave detectors. Understanding dark energy could have profound implications for our understanding of time and the theoretical possibility of time travel. Some physicists speculate that dark energy could be a manifestation of the entropy of the universe, connecting cosmology with thermodynamics on a cosmic scale. Dark energy challenges our intuition about gravity, suggesting that on cosmic scales, repulsion dominates over gravitational attraction. The study of the effects of dark energy on galaxy clusters provides a cosmic laboratory for testing our theories about the evolution of the universe. The possibility that dark energy varies in different regions of the universe has led to the search for cosmic bubbles with distinct physical properties. Understanding dark energy could be crucial to solving other cosmological mysteries, such as the nature of cosmic inflation in the early universe. Advances in quantum field theory and quantum gravity could provide new insights into the origin and nature of dark energy. The study of dark energy reminds us that the universe is stranger and more mysterious than we ever imagined, full of secrets yet to be discovered. As we delve deeper into the mystery of dark energy, we come closer to a deeper understanding of the fundamental nature of the cosmos and our place in it. The search for answers about dark energy continues to drive cosmic exploration, inspiring new generations of scientists to probe the secrets of the universe. The enigma of dark energy reminds us that we are on the threshold of revolutionary discoveries that could redefine our understanding of the universe and its fate. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. At the heart of every black hole lies a mystery, the singularity, a point where space and time lose all meaning. Imagine a place where gravity is so intense that not even light can escape, or matter is compressed to a point of infinite density. The singularity is the limit of our physical knowledge, a realm where Einstein's equations break down and known laws fail. At the singularity, the curvature of spacetime becomes infinite, creating a scenario that our current theories cannot describe. What happens to the matter and energy at the center of a black hole? Is information destroyed or preserved in some mysterious way? The information paradox suggests that anything that falls into a black hole could be lost forever, defying principles of quantum physics. Hawking proposed that black holes emit radiation and could evaporate. What then happens to the singularity and its information? Some theorists suggest that the singularity could be an illusion, hiding a complex structure at the center of black holes. String theory proposes that singularities could be resolved in extra dimensions, avoiding the infinities that plague our theories. The principle of cosmic censorship suggests that singularities are hidden behind event horizons, protecting the universe from their effects. The existence of naked singularities, visible from the outside, remains a possibility that challenges our understanding of causality. Supermassive black holes at the centers of galaxies allow us to study these enigmatic objects and their large-scale singularities. The Event Horizon Telescope has captured groundbreaking images, bringing us closer than ever to the singularity region. These observations test general relativity under extreme conditions, seeking clues toward a more complete theory of gravity. Could singularities be connecting points to other universes? This idea has inspired fascinating theories about wormholes. Some speculate that singularities are portals to other universes, although traversing them seems impossible based on known physics. Quantum physics suggests that near the singularity, spacetime may become discrete or granular, rather than continuous. This granularity could resolve the infinities associated with singularities, providing a more coherent description of these objects. Loop quantum gravity proposes that spacetime has a lattice structure at tiny scales, avoiding real singularities. According to this theory, what we see as a singularity could be a region of extremely curved but actually finite spacetime. The study of singularities forces us to rethink determinism and causality, the pillars of our scientific understanding of the universe. Could the laws of physics change near a singularity? This raises profound questions about the nature of reality. Some theorists suggest that singularities connect our universe to a multiverse, each with its own physical laws. The idea of new physics emerging near singularities inspires the search for theories that unify gravity and quantum mechanics. Mathematical models of singularities have led to advances in fields such as chaos theory and condensed matter physics. This study has philosophical implications, questioning the nature of time, space, and the limits of human knowledge. The possibility that the Big Bang was a singularity connects the study of black holes with theories about the origin of the universe. Could our universe have been born from inside a black hole in another universe, in an eternal cycle of creation and destruction? Simulations of black hole collisions offer new insights into the behavior of singularities under extreme conditions. These simulations suggest that when black holes merge, their singularities could come together in ways that defy our intuition. The detection of gravitational waves allows us to indirectly test the behavior of matter near singularities. These observations could reveal deviations from general relativity, pointing toward a more complete theory of quantum gravity. The study of quantum effects near singularities could resolve the paradox of information loss in black holes. The firewall proposal suggests an energy barrier near the event horizon, challenging the idea of smooth spacetime. Could quantum effects prevent singularities? This has led to proposals such as Planck stars and fuzzball black holes. These theoretical objects would behave like black holes from the outside, but without the problematic singularities inside. The holographic principle suggests that information about a volume of space could be encoded on its surface, offering new perspectives. This idea leads to theories about how information could be preserved in black holes, potentially resolving the information paradox. When studying singularities, we are faced with the limits of our knowledge and our ability to describe physical reality. The enigma of singularities drives the search for a unified theory that describes reality in its most extreme conditions. This mystery continues to challenge scientists, reminding us how much remains to be discovered about the fundamental nature of the universe. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video. Welcome to the Mysteries of the Cosmos. Let us delve into the deepest mysteries of the cosmos, where modern science meets its most challenging limits. What secrets does the universe hold beyond our current understanding? Let's prepare for a journey into the unknown. Imagine a moment before the Big Bang. What was there? This question takes us to the very edge of our understanding of time and space. Surprisingly, the nature of time remains a mystery. Does it flow like a river, or is it an illusion emerging from something more fundamental? In the quantum world, reality becomes blurred. How does our observation influence the collapse of the wave function? The mystery remains. Physicists around the world are tirelessly searching for the theory of everything, trying to unify gravity with the other fundamental forces. We seem to live in a universe fine-tuned for life. Is this a happy cosmic accident, or is there something deeper at play? Looking at the night sky, one wonders, why is there more matter than antimatter in the observable cosmos? A mystery that defies explanation. Within our brains lies another fascinating mystery: consciousness. How does subjective experience arise from neuronal activity? Let's go back billions of years. How did the first self-replicating molecules emerge in the primordial soup of early Earth? Looking up at the stars, we wonder, are we alone in this vast universe, or is life a common phenomenon in the cosmos? Let's reflect on our decisions. In a seemingly deterministic universe, does free will really exist? Cosmic silence. If the universe is so vast and ancient, where are all the extraterrestrial civilizations? The Fermi paradox intrigues us. Delving deeper into the smallest, we encounter the Planck scale. Here, our notions of space and time lose all meaning. Watch an egg crack. Why do we never see the opposite? The mystery of time's arrow defies physicists. Some theories propose additional dimensions curled up in our spacetime. Could they explain some of the enigmas of the universe? Contemplate your existence. Is it the result of a series of cosmic coincidences, or was it somehow predetermined? What if our universe weren't unique? The idea of parallel universes challenges our very conception of reality. Vast magnetic fields crisscross the cosmos. Their origin and maintenance remain a mystery that intrigues astrophysicists. At the heart of physical reality may lie something even more fundamental than matter or energy: information. The vacuum of space isn't really empty. Its energy, related to the enigmatic dark energy, challenges our cosmological models. Is there a limit to what we can know about the universe? The possibility of a final theory in physics remains a matter of debate. Although the Higgs boson explains part of the mystery, the deep origin of the massive elementary particles still holds secrets. At the extremes of the universe, such as in black holes or the Big Bang, our theories of gravity and quantum mechanics collide dramatically. How can quantum mechanics be applied to the entire universe? This measurement problem in cosmology challenges the most brilliant theoretical physicists. Quantum entanglement appears to allow instantaneous connections across space. Does this challenge our understanding of time itself? In a universe tending toward chaos, how do complex, organized structures emerge? This enigma connects physics, biology, and philosophy. Invisible but omnipresent, dark matter shapes galaxies and clusters. Its exact nature remains one of the greatest cosmic mysteries. Step back in time to the early universe. How did the first large-scale structures we see today form? Some theorists propose a bootstrap theory where physical laws emerge from self-consistency. A fascinating and controversial idea. Ultra-energetic cosmic particles are bombarding Earth. Their origin in the far reaches of the universe remains an intriguing mystery. Empty space teems with quantum activity. Understanding its nature could revolutionize our view of the cosmos. Quantum non-locality challenges our intuition about space and time. What does it tell us about the fundamental structure of reality? What if everything we experience is a cosmic computer simulation? This idea, though speculative, raises profound philosophical questions. Observe the turbulent flow of a river. A complete mathematical description of turbulence remains a challenge for physics. The first moments after the Big Bang remain shrouded in mystery. How exactly did the mechanism of cosmic inflation work? At the heart of young galaxies, supermassive black holes challenge our models of formation. How did they grow so rapidly? New particles or forces may lurk beyond the standard model. Physicists tirelessly search for these elusive entities. Cosmic scalar fields, such as the inflaton, may have shaped the early universe. Their exact nature remains a fascinating mystery. At the extremes of the cosmos, gravity and thermodynamics intertwine in surprising ways, challenging our understanding of spacetime. The holy grail of modern physics, reconciling quantum mechanics with general relativity. This challenge is driving cutting-edge research. These enigmas remind us that the universe holds amazing secrets, waiting to be discovered by curious and brave minds. As we explore these frontiers of knowledge, we come closer to a deeper understanding of our place in the vast cosmos. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video.